It is about inertia. And inertia, what's the measure of inertia? Who can tell me? Everybody tell me what the measure of inertia is. Oh, people. Are you with me? Be with me. Listen to the words that are coming out of my mouth and say and talk to me. Everybody, what's the measure of inertia? Mass is the measure of inertia. So Newton's first law is all about mass. Okay? Newton's second law, what's Newton's second law all about? Who can tell me? Acceleration. Newton's second law is all about acceleration. What causes an object to accelerate is force, right? Or more appropriately, what? A net force, good. And we know the acceleration changes depending on what? You said it earlier. The mass of the object. Okay? And so it's a relationship between force and mass. And what's Newton's third law all about? Forces. Yeah. All those together, you can't really have one without the other. They all complement each other. And so because of that, we're going to have a lab next time. In this lab, we're going to get in rockets, not a rocket, but carts that are kind of in the form of a rocket, kind of, okay. And we are going to launch that first rocket as far as we can get it. But we're going to be sitting down. So ladies, wear pants next time. Sound good? I need everybody to participate. So you're going to have a hard time participating with the skirt on, okay? So wear pants. Can y'all do that? Is that something y'all have? I don't know. Maybe you only got skirts. I'm not sure. Okay? And it might be a little chilly, so I know you can't wear a hoodie or a jacket during school, but bring it to class just in case. It might be a little. We're going to do it outside because that's the only place we have to do it. Well, it'd be cool if we did it at lunch in the lunchroom, but it's clear full of tables, right? And they're probably still having lunch right now, are they? Is there still lunch down there? Yeah. So we can't really do it in the lunchroom. All right, so let's talk about forces here. First of all, the attributes of a force. You need to know this. We're going to have a quiz next time that's all about these. And so, ladies and gents, hopefully this will get you to study your notes. We have a quiz next time, and it'll be on the attributes of a force. So make sure you get these down. Can we get it down by next time, you think? There's only 5 of them. And here's what I want you to do. Here's what I don't want you to do. I don't want you to just memorize these. I want you to be able to use your thinker and think about when there's a force, what goes on. So let me ask you some questions that might get you there. So how many objects are present when we have a force? Think about it. Everybody think about it for a minute. Don't tell me. How many objects are present when we have a force? Let's think about that for a minute. How many objects are present when we have a force? And the answer is what? 2, 5, 9, 6. What do you think, Jane? How many objects are present when we have a force? 2. Jane says 2. Who agrees with Jane there's 2? Who says depends? Okay, what does it depend on, Scott? Okay. Give an example where you can push on something and there's 5 objects. that's involved in that force? Yeah. 5 people pushing on a car. Then we have 5 different forces. And with each one of those forces, you have how many objects? 2. The object you're pushing, and you're pushing, you. And you have 5 of those. The next person pushing and the car. The next person pushing and the car. The next person pushing and the car. Do you get that? So how many objects are present when we have a force? 2. Only 2, but 2. Can you have a force without pushing? Without another object? Ready? Watch this. Kyle knows about this. He knows the ki, right? You guys see that force? Was there a force? Yeah, what was the other object? Air. It really was, okay? So, yes, there has to be 2 objects. 2 objects. Write that down. Okay? Yeah, question. What about free fall? Okay, if you're in free fall, then let's see. What object is pulling you to the earth? Well, gravity is not an object. We know gravity is what we call it. Well, what's the object that's pulling us to the earth? The earth. And what's the second object? Us. The object that is falling. So yes, there are always 2 objects. And so remember we talked about force diagrams? And I says, and we had this one right here. I'm going to go up here a little bit. We had an object like this that kind of had motion, saying like this. And some of us drew this, not all of us. Some of us drew this. Right? We drew a force going this way. Is anything do we have a second object that's pushing us that way? No, we don't. Then we don't draw it. Because there's no such force. Are we good? So how is the object able to move then? It has mass, therefore it has inertia. Are you with me? Okay, great question. Thanks for asking. Okay, how many, and I want you to think about this rather than just speak it out, speak your mind. How many forces are present when a force is there? How many forces exist? I want you to think about it for a minute. I want everybody to be thinking about it for a minute. How many forces are present when we have a force? How many forces are present when we have a force? Who has an idea? Okay, Seraphine, what do you think? It depends on how many forces there are? Well, let's say we have 2 objects. Right? Because every time you have a force, you have 2 objects, right? So how many forces exist when we have 2 objects? Think about that. How many forces exist when we have 2 objects? Acting on each other, maybe. Hiram, what do you think? 5. What are they? Gravity, normal force, force of friction, and maybe the applied force. 4 or 5? 4? What do you guys think? Now let's dig a little bit deeper here. What object is causing that force? the surface and the object itself, right? That's two objects for that force. What about this one? The object is one. What's the other object? Whatever's pulling it, right? There's two objects for that force. What's the two objects for the force of friction? Somebody, everybody, one buddy. The surface and the object. Two objects for that one. Well, what's the two objects for the force of gravity? The earth and the object. So that's a lot of objects. What if we just have two objects? How many forces do we have? What'd you say, Priscilla? Well, try again. That's okay. Thanks for trying. What do you think, Serafina? What? One? Well, let's see. I won't pick on you anymore. I mean, I hope you don't pick on me. Go push me, Kyle. Did he push me? Did you guys see that? Oh, that kid. He pushed me. Did I push him? Yeah, I pushed him. How many forces is that? 2. How many objects? 2. We have 2 objects. How many forces do we have? 2. So forces always come in pairs. Not peaches, but pairs. I'm just teasing. You guys understand what kind of pairs I'm talking about? Okay. Forces come in pairs. Let's write that. You'll need to know that for the test or quiz. Come in pair. Is this pair? Right, okay. So we got a bunch of pairs of forces. How many pairs of forces do we have in this scenario? 4 pair of forces, right? Okay. All right. Now let's talk about the pairs of forces. I'm going to erase this because if we have a pair of forces, which one is stronger? Is it the one that decides to do the pushing, or is it the one that gets pushed? Which one is stronger? Think about that for a minute. Which force is stronger? The action force or the reaction force? Think about that. All right, let's go with Cadence. What do you think? If I push you, did you push me? Should we see? Do you know? Did she push me?
Oh, I did.
I felt it on my hand. I did. I felt a push on my hand. So, which had more force? Me pushing you or you pushing me? I pushing her. She says I'm the bully. What do you guys think? Am I the bully or is she the bully?
She's the bully.
Or it's just even, right? So next time your brother or sister is bugging, it's like, if you don't quit bugging me, I'm going to smack you. Hope you guys don't do this, right? But maybe when you're littler, right? If you don't quit bugging me, I'm going to smack you. And what do? They keep bugging you because it's funny. It's not like I'm going to keep bugging, right? And you go, whack! You smack your brother or sister, and then what happens? Mom! They run over. You say, why did you do it? And what can you say?
He hit me.
But my brother hit me too. We're even, right? No, we don't try to argue with our mom and dad, but I'm just saying. So who pushed harder, me or Cadence? Same. Should I prove it to you?
Yeah.
All right. What? Take your dominant finger, whether if your right hand dominant, that's your dominant finger, okay? And your non-dominant finger, and I want your non-dominant finger to just stay there, and I want you to push your fingertips like this. So you push with your non-dominant, but I don't want you to break your other finger. Okay? I don't want you to break your other finger. Push it for a minute, and then look at the colors of your fingers. Which one is more white? They're the same. Same. So when I pushed Rachel, she pushed me the same. When I pushed Caden, she pushed me the same. When I pushed Kyle, he pushed me the same. Are we good? So why then, if you slug somebody in the face, does it hurt the person that gets punched in the face more than it hurts you? Does it? Hopefully you guys don't know, but if you punch somebody in the face, does it hurt you? Yeah, it hurts your hand. It really does. Why does it hurt the person's face more than it hurts your hand? Your face is more sensitive, isn't it? Okay? But is it the same force? Yes, and that's why it hurts your hand. You ever slug? Hopefully you didn't. Because when I was in middle school, then I was public school, middle school, you know. I guess this is public school, but anyway. Kids think they're tough. They're, yeah, and they go and run and smack into the locker. I'm tough. Oh. Okay. Did it hurt them more or the locker more? Probably them. The locker's just laughing, right? Okay. So why then, so let's say if I push this wall, and the wall pushed me, did you guys see the wall push me? Yeah, did you see me move back? Who pushed harder? They're the same? Then why did I move clear back and the wall didn't even move at all? Because the wall has more mass, therefore it has more inertia. Has a greater tendency to want to just stay there, right? And I have less inertia, so I'm going to move more. Or we get especially with the wheels, right? Does that make sense to everybody? So the pair of forces are equal in magnitude. What does magnitude mean again? Amount or strength in this case, right? Equal strengths. No matter what. This is a law, ladies and gents. Okay? And if I push on the wall north, the wall pushes me which way? South. Every time? Is it always opposite? Always. I push on Rachel that way. She pushed on me this way. Okay? I won't push again. Okay? So forces are opposite, always opposite in direction. Because we know force is a vector quantity, right? It has both magnitude and direction. Same magnitude, and opposite directions. Are we good? We're writing this down? Should. Let's do. And the last attribute, so that's, we got 1, 2, 3, 4, and the fifth attribute is what? If I push Rachel, you saw that she pushed me. Who pushed who first? Same time, right? Forces are simultaneous, or they occur at the same time. Yeah. You mean this way? So here's our 5 attributes of a force. Any questions on those? Do they have to be in that order? No. Can you remember them by just thinking of forces? Think about me and this table. I push on the table. How many objects are there? 2, me and the table. I push the table that way. The table pushes me which way? This way, opposite way. I push the table with 10 newtons, it pushes me same amount. Why do I move more? Less inertia, right? Less mass, less inertia. And if I push at 2 o'clock in the afternoon, or 1 o'clock, what time do they push me? 1 o'clock, same time. You get that? Can you remember that without having to, let's see, I know there's 5 of them, what are they? Can you think your way through it? All right. Any questions so far? How are we feeling? Pretty straightforward? Or is there anything like, that doesn't seem right? Anything? Okay. All right, here, let's have some, you guys like things to be more fluid than just boring, sit and listen? Who would rather get up and do something? Okay, so Sarah, why don't you come up here? You stand right here. Now watch. Does it take that much force to break this paper? Not that much at all. Just a little bit of force, right? Do you think you can punch harder force than I use to rip this paper? You don't think so? Come on. You never punched your brother? Oh, she's a good girl. Okay. Think you can punch a hole in that paper? Try it. Hard as you can. Oh, was that as hard as you can? Oh, come on. She just doesn't want to show off. Okay, thanks, Sarah. Any guy think they can punch a hole in this paper? You want to try it? Yeah, come on up.
I was just going to say, hold the top of the bottom and
Come on, just hold it like this. Hang in midair. Can you? Can anybody? Anybody want to get a shot? Sitting there, that's no fun sitting there. Was that funner coming up here? Yeah, she's way fun. She's even smiling. Okay. No, you want to try, Scott? Come on up. You can try it if you can do it. What do you think? Can you do it? Okay, hit it. Don't punch me in the face. You almost, I felt it right here, but you didn't hit me. It was all that air. Be careful. Dude. Yeah, he's a wimp. Sit down. You want to try it? No, I want you to punch it with your...
I don't think so.
No? Okay, now, do you think anybody can do that? What about Mike Tyson? I don't know if Mike Tyson's 80 guys, but he's a boxer, and okay, he's a tough boxer. He's so tough he can fight somebody's ear off. I don't know if you've ever heard of that guy, but recently there was the top boxer guy who wanted to fight Mike Tyson, and he lost to Mike Tyson. Mike Tyson's old. Okay. Do you think anybody can break a hole of this? Why not? That's the question. So, we learned the 5 attributes. Why not? Think about that. Just think for a minute. Why can't you, let's say it only takes 1 newton of force to break this paper. I know Kenneth can hit stronger than 1 newton of force, but he can't break it. Or do you think he can? No? Okay. Why not? If it only takes 1 newton to break this, why can't we? Let's say that we could break a hole in it. And maybe there's a possibility. Because Chris said, can I use a pencil? Think you can do it with a pencil? Okay. So maybe do you think Chris can hit it with the pencil with 100 newtons of force? Forget about 100. Can he hit it with 2 newtons of force if it only takes 1 newton of force to break the paper? Could he? The answer is no. Why not? Think about the 5 attributes of a force. Why can't Mike Tyson hit this with as much force as he can hit somebody's face? Why not? Go ahead. More fundamental than that. More fun. If I was hanging a guy, could Mike Tyson punch this guy in the face and make it hurt really bad? Yes. Can he hit the guy with more force than he hits the paper? Yes. A lot more. Why? Can he only hit up to 1 newton of force? If it takes 1 newton of force to break this, why can he only hit up to 1 newton of force?
Because it doesn't break.
Go ahead.
I'm sure that's a change.
No? No? Yeah, Serafina.
Because when you try to go in opposite directions, it's when you punch it down.
So what?
When you turn, it's going in opposite directions, but when you punch it, it's going in one direction.
It hit me in the opposite direction.
The paper moved out.
Sure. Would the guy move if I hit him? If he was hanging? Yeah, he'd move. Why can't he hit this paper with more than 1 newton of force? Because you can't hit back with that much force. Can't hit back. And that's the law. If I hit an object, it has to hit me just as hard. Do you get that? And what happens if this hit harder than 1 newton? Then you would win the Nobel. It would win the Nobel Prize. Yeah, it breaks at 1 newton. That means only hit with 1 newton of force, and then it breaks. Then your hand goes through it, and you're no longer hitting it anymore. Does that make sense? Yes? No? Talk to me. The law says the 2 forces have to be equal in magnitude. If the object can't hit back with that much force, you can't hit it with that much force. Good? I don't know if we're good. 5, if we get that, we understand that idea. And 1's like, that still doesn't make any sense. Show me. 5, you get it, 100%. 1 is, no. Somewhere between. Okay, good. All right, now we need a stretch break, right? But rather than just getting up and stretching, let's get up and play a game. And this is called the game of physics. Who wants to get up here and demonstrate with me how to play this game? Okay, come on up. Stand right there. And when you stand, I want you to stand just normal. Not your feet clear out here, not your feet close together, just normal. Just stand normal. So face me. And I want your toes, they don't have to touch, but somewhat close together. Right? And you can only touch hands. So put your hands out like this. You can only touch hands. Right? You can't touch shoulders. You can't grab their hands and pull. You can only push on hands. Pat a cake, right? And the goal is to get the other person to lose their balance. Are we good? If you tip over, you don't have to fall and hit your face, but if you tip over, lose your balance, you lose. Are we good? Extra credit to the winner of the guys, extra credit to the winner of the girls. And if the girls can win the guys, double extra credit. But I'm not going to go the other way for the guys, okay? Okay. So girls, you go against girls. Guys, go against. I need everybody to participate here. And then we'll have the champion guy go against the champion girl. For double extra credit. So get your feet close together. They don't have to be touching, but.
Oh, I almost did it right.
And take turns. Find somebody. There you go. And you're out if you lose twice, I guess. So keep trying. Kyle, put your legs, feet a little bit close, not close together, but just regular. There you go. Oh, she lost her balance.
My sister did paint my hair. Anybody want to try to beat Kyle? He's the champion guy so far. Guys, try to beat Kyle. He's the champion girl so far. Get a little closer. Come on, go to something else. You're only going to try here. Did you win? Okay. Did you lose? You won? Okay, try this gal. Right here. Did you try everybody over here? You want everybody over here? You want her? All right. Go again. Hey, what the? Oh, I lost. So, you have to let your hair? Okay, Rachel, right up there. You understand one? Okay, go for it, Rachel. Yeah, that's one. That's round three. Yeah, that's what if you want to you only lost one pair. Yeah, try it.
I guess you don't know.
Okay, you go against her. You want to try her again? You can do it. It's possible. Get closer.
That wasn't hard.
Oh! Okay, that's 1-1. It was me. I was saying that. Oh! Okay. You want to go against the board?
I won every.
So you want to turn it down? You want to go?
Actually.
Okay. Who's the champion guy? Kyle, what? Looks like you don't want it. You don't have to have it. You want to give the next person?
Oh, it's actually what?
Extra credits for the winner.
Yeah, I'll do it.
Okay, so we got extra credits. So far, you guys got extra credit. Now come up here. Right here. Okay, let's see it. Best 2 out of 3. Best 2 out of 3. Okay, you don't have to get real close. Get a little closer than that. A little closer. Okay. Go ahead. Okay, there's one. There's one. That's just one. Oh! Here we go. Let's go. Come on, Rachel! Come on, Rachel! Last chance. Oh, you didn't yet? You didn't yet? That was my elbows. Sorry. Oh! Double extra credit. How'd you lose? All right, hold on. Now I gotta try Rachel. Right here, Rachel. If I win, then I get to take one.
But you bring some off.
No, putting brakes on is cheating. That means she's got a bigger advantage, right? Oh, she's moving yet? Moving me. How do you lose?
You like measure how much you roll?
Oh, come on. Come on. I'm going forward. I don't go back. Well, okay, she's champion of the world. All right, go sit down. So I've seen some of you guys win because there was no force at all, right? You go like this, and they move back and you fall, okay? So it's not just who can hit harder, is it? Push harder. There's other factors. Okay, are we good? But it looks like both times that either one of these lost, it was because they pushed harder than the other. Is that right? No. Did anyone ever push harder than the other person? No. No. So that is not how you do it.
Sound good? So that brings us into the next idea. Okay. How do you win a tug of war contest? Think about that. How do you win a tug of war contest? More inertia? Let's say both teams have the same amount of mass altogether. Now how do you win? What? Structure, what do you mean? Don't stand up like this, but stand like this. Okay, yeah, hopefully everybody does that. It's like, you guys ever shoot a shotgun like this? Stand up straight. It's gonna knock you over, right? Okay, okay, so you have, your stance has to be good. And that's, I think everybody would have a good stand. They're not, if they're just pulling, okay, I'm pulling, then they don't really want to win, right? So, okay, so the stance has to be there. How can you, what's the most important thing you can do to win a tug of war contest? Use the normal force? What do you mean? Okay, so you weigh more? You weigh more? Oh, you push more on the floor? Why would that make you win? Oh, who has more inertia, you or the floor? The floor does, so who's moving? You are. If you push the floor back, it pushes you forward, right? Or if you push forward, it pushes you back, right? Yeah. What's that? A quick, okay, you can have a quicker reaction on your mark, set, go, and pull faster than they, okay. That's a good technique. Get them off guard. Yeah. But the biggest thing is pushing on the floor. Does everybody understand why? No? Okay, if we pull a rope, and it's tight, who's pulling harder? They're the same. That tension in the rope is how much force that is being applied on both teams. You with me? So you can't pull harder than the other team. You just cannot. But if you push on the ground, just like me pushing against this wall, the wall doesn't move because it has a lot of inertia. The ground won't move because it has a lot of inertia. Instead, I move. So if I'm pushing on the floor this way, the ground is pushing me back. And that's the direction we want to go. Do you get that? Should we try it, or are we good with just talking about it? Okay, let's see. Let's split this down right here. So Priscilla, you're on this side. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's okay. Yeah, Priscilla, you're on this side. Angela, you're on this side. You guys are on one side, and you're on the other side. So we have 5 guys over here, 4 guys over. Yeah, it's pretty even, right? Why do I say guys and gals? Are guys and gals different? Are they guys, gals different? Yeah. Who generally has stronger legs? The guys do. That has nothing to be sexist or racist, right? It's just how we're built. We're different. And okay, I won't go any more than that. But anyway, so that side and this side. So we're gonna go down by the lockers by Mr. G's class. Mr. Ken's class. but we're not going to be real loud over there. And if his door's open, maybe we'll close it so that we don't make noise. Okay? Okay, let's go. Any questions about Newton's third law so far? Okay, let's make sure we know what Newton's third law is. Write this down in your notes. So the quick and simple way is for every action there is an equal and opposite reaction. But that's kind of missing a lot of information, isn't it? Or it's kind of assuming that you know what's going on, yeah? So let's write it in different words. When one object exerts a force, you guys know what that word means, exerts? Applies a force. Okay. When one object exerts a force on a second object, the second object exerts an equal force on the first object in the opposite direction at the same time. When one object exerts a force on a second object, the second object exerts an equal force on the first object in the opposite direction at the same time. Do we have all 5 attributes there? First attribute. How many objects? 2 objects. First object, second object. Good? Okay. What's the second one? The first and the second object exerts an equal force, right? And equal mean equal in magnitude, right? Opposite in direction. And at the same time. Are we good? Okay, you have a worksheet that you picked up. On the front side where it says 7-2, it kind of demonstrates how to do this. The fist hits wall. That's the action force. What's the reaction force? Wall hits fist. And notice, there's an arrow from the fist going toward the wall and an arrow at the fist going toward the fist, or where they meet, going toward the wall and toward the fist. Yeah? Opposite direction. And how do you show that they're equal in magnitude? Same length of arrow. There's some of these are going to be on the quiz next time. Which ones I'm not going to tell you. So make sure you understand all of them. There are some on the quiz. You have this? That paper right there. We're working on that paper. Do we have any questions on how to do this? Okay, take a minute. Oops, sorry. Any questions on number 1? That's all of those action-reaction pairs. Yeah. Letter H. Letter H says, can I see that? Oh, you just pick your own. Make up your own. Any other questions? All right, this next says, draw arrows to show the chain of at least 6 pair of action-reaction forces below. So who wants to get, let's see, let's have Jason. Give me one action-reaction pair on this, on number 2 here. Guy pushing on the ground. That's the action pair of the pair. Ground pushes opposite direction on the man, right? Okay, so there's one. Chase, what's another one? Real loud? String pulling on the, or rope pulling on the tree. And what's the reaction? Tree pulling on the string, right? All right. There's 2. We need at least 6. Let's go with Jennifer. What's another one? What's an action-reaction pair on this? Real loud? The string pulling on what? Yeah. So the string's pulling on the guy, and the guy is pulling on the string, right? Perfect. There's 3. Let's go with Rachel. What's one? One more.
Could you do the monkey?
Which hand?
Right.
Either hand, right? So there's 2 pair right there. Any others? That's 1, 2, 3, 4, 5. We have to have at least 6. Are there only 6? What's another, Jaden?
That way thing.
The what thing?
The thing between the tree and the monkey.
Oh, yeah. We'll just ignore that one. Because what we're saying here is this has a certain tension. Maybe it's 100 newtons. And that. Oh, the tree and the ground? So what do we call this? The weight of the tree and the tree pulling up on the earth?
Yeah.
Is that true? Okay. What else? We have at least 2 more. Go ahead, Chris. Yeah, the weight of monkey. And what's the other one? The monkey pulling up on the earth. Is that right? Now, ladies and gents, I'm probably drawing these. Yeah, that's okay, I guess. Am I drawing force diagrams? I am not. I'm drawing the pairs of forces. That means there's 2 objects. When I draw a force diagram, how many objects am I worried about? Just 1. You with me, guys? So I'm not even labeling these because it's not a force diagram. Make sure you understand that. That's where a lot of people make mistakes. These are not force diagrams. These are just the pairs of forces, the action-reaction pairs. There's one more. Where is it? The guy's weight and the earth, him pulling up on the earth. Is he pulling up on the earth? How much? Same as his weight, right? That's Newton's third law. Do we get in this, guys? Or am I just talking? Okay. I just mostly want you to do the front side. Let's see. Back side is kind of helping you understand the difference between the action-reaction forces and a force diagram. You guys remember force vector diagrams? We're drawing all the forces acting on one object. That's what a force diagram is. But an action-reaction pair are the two forces caused from two objects. Good? All right. Let's stop doing that for a minute. Any questions on the front side before we move on? No, we're good? All right. So now let's say we have this big old truck. Okay. With this trailer on it, right? Big old truck. And then we have, can you guys all tell what this is? A smart car. Doesn't that look like a smart car? Just a little bitty guy. All right. These guys head-on collide. Head-on collision. Which one hits the other one with a greater force? Who says the Mack truck hits harder? Good. It's because it's the smart car that hits harder, right? I'm just kidding. Same, right? So then why does the smart car get demolished? Go ahead. It has less inertia. Thank you. Yeah. You want me to? Okay. So yeah, it has less inertia. And okay. Even though it's going faster? Does inertia depend on how fast you're going? No, it depends on mass. Okay. What about a bug hitting the windshield? Which one hits harder, the bug or the windshield? Then why in the heck does the life of the bug is done for? Smashed. You don't even know it's a bug. It looks like blood or guts or whatever. Why is it the same? Because it's the law. You with me? And it gets demolished because it only takes a little bit of force to demolish that bug, but a lot of bit of force to demolish that car, or even crack the windshield, right? So the force can't hit as hard because it can't break that windshield. It takes less force to demolish it. Kind of like the paper hanging in the air, right? Same thing. So in this this big old Mack truck and this little smart car, what direction will the two accelerate after they crash? Toward the right or toward the left? What do you think? Toward the right, because I need one person to raise your hand and tell me why. Go ahead. Okay. But why is it to the right? Go ahead.
The truck has more force.
No. They're the same force. Actually, I kind of got mixed up in my head. Yeah, you're right. You're right. It's because it has more inertia. That's why. Okay. Are we good? Which one will have a greater net force on it? The car or the truck? Yeah. The truck will have a greater net force? Then why doesn't it get hurt? It almost, do you get that, guys? The car feels a greater net force. Therefore, which one feels a greater change in velocity or an acceleration? The car does. Newton's second law says net force is directly proportional to the acceleration, right? Okay, one more thing. Hold on. I got to tell you this. Next time we're having a lab, right? Doing a lab? So pay attention. You can think about this. Here is what we're doing next time. I need you to pay attention real quick. I'll give you time. Just be with me. So we have these carts set up like this. And these carts have wheels on them. This is cart 1, 2, and 3. All with me? Kyle, be with me. Everybody with me. Don't put your stuff away. Quiet. Just listen. Okay, we can only put one person on cart 1. And this is our pilot to our rocket. You can put the rest of the people on carts 2 and 3. You cannot push off the ground or anything that's not completely on the carts. You with me? That means you can't push the ground to get that thing to go. If there's a wall here, you can't push off the wall. You can only push on something that is completely on the cart. And if you're completely on the cart, you can push on the cart itself. But you cannot touch the ground while pushing. You follow? Think about how you're going to do that. Extra credit to the team that wins. Hey, ladies and gents, have a great day. Thank you. You're only going to be here 10 minutes? Dang it. It's going to be a fun day.
Finish class, second grade today.
Second period today? No. I have one tomorrow. I have one during first and fourth period. Hang on, I'll try to sort this. Sound good? I don't have time to fly for today,
This is a action.
No. No, that's the force vector diagram. The action is the hand pushing up on the apple. The reaction is the apple pushing on the hand, or vice versa.
So we cannot say it's supposed to actually say and another pair of action. Actually works separately. So this is not an action. Yeah.
Another pair of forces is shown, and the downward force, yeah, that's right.
And after this, Sorry.